Have you ever wondered if an unsolvable math problem could actually explain the eerie silence of the cosmos? It is a massive existential question, right? Well, today we're going to look at how a literal physical anomaly in orbital mechanics, specifically how the three-body problem actually works, scales all the way up to a downright terrifying theory about why we haven't found any alien life yet.
Welcome to this explainer. I am absolutely thrilled to guide you through this today. We're going to explore the fascinating science, the chaotic physics, and the mind-bending sociology behind the three-body problem. Okay, let's dive right into this.
So here is our roadmap for today. We'll start by looking at the massive pop culture footprint of this concept before zooming right into the mechanics of how the actual physics works. Then, we'll explore a rare cosmic exception to the rule, connect the science back to the famous sci-fi narrative, and finally zoom way out to the chilling dark forest hypothesis.
Starting off with Section 1, a pop culture phenomenon.
Before we really get into the nitty-gritty of the physics, it is definitely worth appreciating how this whole concept has completely captured the globe's imagination. I mean, what started as Chinese sci-fi author Liu Cixin's 2008 novel series just exploded across all sorts of mediums. We've got a 2023 Tencent TV series, a Bilibili animation, and of course that massive 2024 Netflix adaptation. Communities on Reddit are constantly buzzing, debating fan theories and character arcs that span literally hundreds of years of the story's timeline. Millions of people have been sucked in by the fiction, and now, they really want to understand the actual science behind it all.
Which brings us to Section 2, how the physics works. Long before this was a hit TV show, it was actually Isaac Newton's first real worry. And to understand why it stressed out one of history's greatest minds, we have to ask a really fundamental question. What happens when you add a third? You see, the physics of a two-body system, think of a single planet orbiting a single star, is pretty straightforward. They exert gravitational forces on one another, usually orbiting in a nice, predictable circle around their center of mass. They always come back exactly to where they started. But when you add a third massive body to the mix, well, everything just breaks down.
In a two-body system, everything is predictable, stable, and cyclical. It just works. But in a three-body system, things become incredibly chaotic. That third body essentially crashes the party. It attracts the two bodies that are already orbiting each other, pulling them entirely out of their predictable paths. And here is the core of how the three-body problem works. Because you are constantly tracking the ever-changing distance, mass, and velocity of three completely separate objects that are all acting on each other simultaneously, there are actually more variables of motion than there are constant mathematical laws to constrain them. The resulting motion relies entirely on their starting state, their exact positions, their velocities, and their masses at the very beginning.
Applied mathematician Shane Ross perfectly captures this extreme sensitivity. He says, I think of it as if you're walking on a mountain ridge. With one small change, you could either fall to the right or you could fall to the left. Because the math here is just so insanely sensitive, if even one tiny microscopic variable changes, the resulting planetary motion could be completely different. Over time, those shifting gravitational forces could cause two of the bodies to smash into each other or even fling one of them completely out into deep space.
Moving on to Section 3, the rare Tatooine exception. Now, if the math is that incredibly chaotic, you're probably wondering, how in the world do any planets survive in multiple star systems? Well, it turns out that under very, very specific conditions, the math actually can be solved. Scientists have actually found over a dozen exoplanets that orbit multiple suns. A super famous example is Kepler-16b, which orbits two suns, making it look a whole lot like Luke Skywalker's fictional homeworld of Tatooine. But how does this system manage to avoid the chaotic doom of the three-body problem? Well, it basically comes down to what we can playfully call the fat star exception. Planetary dynamicist Billy Quarles points out that if a planet is far enough away from a central binary star pair, you can mathematically treat that central pair as just one really fat star, because that distant planet is so much less massive, it simply doesn't exert enough gravitational force to throw those two central stars into chaos. So that vast distance actually simplifies those chaotic three bodies right back into an easily solvable two-body problem. Pretty neat, right?
Let's jump into Section 4, the Trisilurian sci-fi connection.
So how does author Liu Cixin take this brutal physics and actually use it in his narrative? Well, in a really memorable virtual reality sequence, his characters visualize the exact physics problem like this. Imagine one sphere hanging in an infinite void, totally motionless, a symbol for death. Then add a second sphere, and gravity pulls them into a stable, unchanging orbit, the dance of death. But then add a third sphere, and suddenly the void just bursts to life. The spheres go through these incredibly complex, never-repeating movements.
The descriptive equations literally rain down like an endless thunderstorm. And this, my friends, is the tragic, chaotic reality for the Trisolarians, an alien race in the Alpha Centauri system desperately trying to survive on a planet that's just caught between three chaotic suns.
Because scientists agree that a three-body system is definitely not a stable environment for life to evolve, the Trisolarians know, without a doubt, that their planet will eventually be completely swallowed by one of their suns. So, when a human physicist named Yi Wenji broadcasts a message out into the cosmos back in the 1960s, the Trisolarians hear it. Realizing Earth is basically a stable paradise, their fleet mobilizes immediately. But they're limited by the speed of light and their current tech, which means humanity has exactly 400 years before that invasion fleet arrives on our doorstep.
And that takes us to our final part, Section 5, the Dark Forest Hypothesis. This is the point where we zoom way out, moving from the literal physics of planets to the grand sociological game theory of entire civilizations. In this story, Yi Wenji imparts the core axioms of what she calls cosmic sociology to a character named Luo Ji. There are four really crucial assumptions you need to know here. First off, survival is the absolutely paramount goal of every single civilization. Second, the universe's resources are finite, which essentially forces civilizations to relentlessly expand. Third is the chain of suspicion. And fourth is the technological explosion, which warns that an alien race could undergo a rapid jump in technological advancement, turning what looked like a primitive ally into a massive existential threat practically overnight. Let's look a bit closer at that third axiom. The chain of suspicion is basically an endless, unbreakable loop of mistrust. Because of the truly massive distances in space and the absolute speed limit of light, you can never quickly communicate with another civilization to figure out what their true intentions are. So the crucial point here is that this sociological concept perfectly mirrors the chaotic unpredictability of the physical three-body problem. Just as you can't predict that third star's orbit in physics, you absolutely cannot predict another civilization's intentions in sociology. When we map this all out into a game theory matrix, the truly terrifying reality starts to set in. Imagine for a second you detect another civilization. You really only have two choices: hide or attack. If both of you hide, nothing changes. That's a 0-0 outcome. But if you hide and they attack, your civilization is completely wiped out, giving them a massive advantage. And because of that chain of suspicion and the constant fear of a sudden technological explosion, you basically have to assume that they will eventually attack you. Therefore, mathematically speaking, the only rational dominant strategy to ensure your own survival in such an uncertain cosmos is to remain completely, utterly silent, or launch a preemptive strike against anyone foolish enough to reveal their location. And that brings us full circle back to our opening puzzle, the Fermi paradox. We know there are billions of planets out there, so where is everybody? Well, the dark forest hypothesis suggests the universe isn't empty at all. Rather, it's like a vast, shadowy woodland teeming with heavily armed hunters. Every civilization out there is terrified of the chaotic variables of contact. Broadcasting your location is literally like shouting in a dark forest. It just invites a swift bullet from the shadows. So I'll leave you with this to ponder. Next time you look up at the stars at night, is the eerie silence of the sky due to a lack of life, or a universe full of hidden hunters? Thank you so much for joining me on this explainer. Keep your eyes on the stars and stay curious.